Hey YouTube, you're looking at the Teledyne LeCroy HDO4024, a 12-bit oscilloscope with 200 MHz bandwidth. I already did a teardown of this oscilloscope on my text blog and had 2,500 views within the first 24 hours. And that tells me that there's really big interest in a teardown of this oscilloscope, so I decided that video is always a little bit better than text, and I will tear this oscilloscope down for you on video. As you would expect, the back side of the oscilloscope is not very spectacular. You got your power input, it's rated for 100 to 240 volts, 50 to through 400 Hertz. I mean, obviously it's using a switch mode power supply, so the frequency doesn't really matter. But that's pretty much it. You got your 10 megahertz reference in and out. Why does it have in and out on there? The explanation is actually very simple. You can either feed a 10 megahertz signal into the scope as external reference, or you can use the scope as a reference signal generator for other devices that you may have around. That's probably interesting if you cascade several oscilloscopes to capture something. If I don't know what you would do, but certainly there are scenarios where you want to cascade several devices, and if you don't have an external frequency source available, well, it may not be very accurate, but it's certainly precise if all instruments are clocked to the same reference. You got an auxiliary output. You can actually determine in software what you want to put there. I think the default is obviously a trigger output, and over here you can see a model number. Mine is an HDO4024. That is the 200 megahertz version of the HDO4000 series. There's a 200, 350, 500 megahertz and 1 gigahertz version. I have no idea why Teledyne LeCroy tossed in a 350 megahertz option. That's an unusual step, and turns out the 350 megahertz version is only $500 more expensive than the 200 megahertz option. By the way, the scope is not very expensive at all. The version that you see there on the table without option, it's available for just under 10 grand, which for scopes, high professional scopes is pretty decent price. I mean, you can compare this to your Rigol scopes that you may be using in your home labs. Alrighty, the scope's obviously consuming 340 watts of power. That's not too bad, and a bunch of patents, of course. Being in the United States, or being a United States manufacturer, LeCroy probably gets a patent on anything that they can get patent. Would be interesting to read actually up on them. Well, anyway, one's under license, and that pretty much concludes the backside. You can see the big fan opening here. You can see another fan right there, and I don't know if the camera catches that very well, but you can actually see a PC mainboard behind that grid, and there's another fan up here. As you can see, I already avoided my warranty. Well, actually, it only says calibration void if seal is broken, so if you wanted to be a legal smartass, you could argue it never said that the warranty is void, but then again, it probably says so somewhere in the warranty terms and conditions that you can't take it apart, but who cares? Let's open it up. That's what the scope looks like with the cover removed. It's actually a pretty solid metal shield, and you can hear it. That thing is rock solid, and not some floppy thin metal shielding like you see in some of the devices around nowadays. So let's remove the shield and have a look under cover. And here you go, that's the scope opened up. Over here is a standard computer motherboard. I couldn't really find a manufacturer name on this board anywhere. If you spot it on the video, please let me know, but I didn't see anything useful that pointed to a manufacturer on there. Over here is the switch mode power supply. Fortunately, I mean, I guess I could open it up, but I don't really want to. It's just a plain ordinary switch mode power supply. You see a single voltage supply coming down here. to the acquisition board, and you see that they apparently looked a little bit at mechanical stability. Just about any wire that you see in this thing is really tied down somewhere. You know, there's nothing just loose. Even those PCIe connectors, even though the tension on the slot should probably be enough to hold them in, there's a little bracket on the back that's holding it in place. Let me actually get the camera out of its stand and look around a little bit. Alright, start in the back. Those two connectors here are your two BNCs from the back. You have your trigger input slash, no, not input, sorry, output, and your 10 megahertz reference input slash output. Your USB connector right over there, and there's your power input. There's obviously a varistor down there for transient suppression, and right there it goes into the switch mode power supply. There's a big fan in front of it, just for the switch mode power supply. There's a big center fan blowing down on the FPGAs. We'll look at the acquisition board in a second. And over here is your computer main board. Now, as I said, I don't see any manufacturer's names on it. Who knows? Maybe LeCroy will let us in on the secret who the manufacturer is. Right here is some 2 GB RAM. It's actually not very much for a scope like that, but it does seem to be enough. Over here, this little card is a PCI Express to USB host bridge. Very simple design, and that's pretty much it on the top layer. So I'm gonna remove that layer and enable us to take a look at the acquisition board down there. Okay, now you got an unrestricted view onto the brains of the oscilloscope. This is where it all happens. This is where all the processing and handling of the data happens. The data acquisition itself, clock generation, and all the good stuff. Right here you got your front ends for channel 1, 2, 3, 4, and the external trigger input. Got the ADCs right here, also for the 4 channels and the external trigger input. 2 FPGAs per channel right here. Got your SD-RAM for the FPGAs next to the FPGAs. There's more over here. They don't have a heatsink. We'll talk about why those have a heatsink and those not a little bit later. In the middle is an ASIC responsible for timing and making sure that everything is neat and time coherent in this oscilloscope. This down here is the PCI Express connector. It's connected through to the motherboard with that little PCIe bridge that we've seen earlier. And in my blog I mistakenly stated that I believe this NXP processor down here to be in charge of handling the PCI Express traffic. And I made that statement without even reading the data sheet, and it turns out that this chip simply doesn't have the horsepower to deal with PCI Express in any way. So I want to correct that and blame this FPGA over here for PCI Express handling. Back here's the RF section, the clock generation and clock distribution for the oscilloscope. Right down here is a 125 megahertz crystal oscillator from Crystec. Crystec claims a very low phase noise for this particular oscillator. This coax down here is the 10 megahertz reference input, and over here is the clock generation and distribution. And we'll see where that goes in a little bit here. You see some expansion slots. Here's one there, and you see this little cutout down here. That's actually where the digital option slot is on the front of the oscilloscope. So therefore I assume that those expansion slots are exactly for that purpose, for the digital option to be added on later on. Like I said previously, the acquisition board has a single voltage power supply. There's a little bit of power coming through another connector from the motherboard, but I think this is pretty much irrelevant for the majority of the board. There's a single voltage power supply, and you have some voltage regulation and power conditioning around the connector. So I guess this board pretty much does all this power conditioning by itself and does not rely on the power supply. Very good. Down here's a 14-pin connector, and 14-pin with a couple of line drivers behind. Sounds to me suspiciously like JTAG. I wonder if it would be possible to read and write from or to this device, but I'm not gonna bother trying to decipher whatever they have in there and trying to change it, even though it would be very interesting to see if this scope can be hacked. As I said, this is the 200 megahertz version, and I wonder if it can be modified to be a higher frequency version. And this sticker back here actually leads me to believe that it should be possible. If there were a huge hardware, or if there was a big hardware difference to the higher frequency versions, then you would expect this to be printed onto the silk screen in some way. But they actually just put a lousy sticker on there saying this is the 200 megahertz version. So either somebody forgot to put the 200 megahertz version information in the silk screen, or it is actually as simple as changing the software to get a higher frequency version. Well, I guess we'll never know unless somebody wants to mess with it. Okay, let's see. What else we got? There are 2 FPGAs per channel. There's a little bit of SD-RAM on each side of the FPGAs right here. So you would assume that maybe this FPGA down here is responsible for getting the data from the ADC. This one up here is responsible for storing and processing the data. On a side note, this one has a storage capacity of 25 megapoints or interleaved, or 12.5 megapoints if all channels are active. And you can get 25 megapoints standard and 50 megapoints interleaved, but that's a software option. It's a bloody software option. The hardware isn't different, so you're getting the exact same hardware, but you have to pay a little bit of money to get the extended memory capabilities of this oscilloscope. Now you can clearly see the differential pair going from the ADC to the FPGA down here. It's channel 1, same here on channel 2, and channel 3 and 4 are a bit longer, and that's what all these thingies here, all these curvy things are about. They need to make sure that the time integrity between all channels is 100% guaranteed. So to do that, you need to make sure that the distance, the electrical distance from ADC to FPGA, is exactly the same on each channel. So here you have a relatively long lead, and here the distance is short. So you need to introduce some extra length artificially by adding those curvy things on there. It's, you see that very often, particularly in high-speed data applications. Very neat, nice to see. Alright, let's see over here. That's channel 3 and 4. Same scenario here that you've already seen channel 1 and 2. 2 FPGAs per channel, SD-RAM over here, and SD-RAM over here. You may notice something. Look, the SD-RAM in the center and to the right has heatsinks on there, and the SD-RAM over here does not. Why is that? Well, the answer is simple. The fan is actually located about right here, so you don't really have a thermal problem here, but the flow, the airflow over here is more restricted than it was in the channel 1 and 2 section. So you need to make up for that and put in some heatsinks. Now what you see right now is probably the most important part of the oscilloscope. Under this metal cover you'll find the RF front ends for the input channels and the external trigger, and right here are the corresponding ADCs. The ADCs are 12-bit ADCs, like I already mentioned before, and even though Tektronix argued, or a Tektronix employee to be precise, argued in a ridiculous blog post that their oscilloscopes, their 8-bit oscilloscopes, could measure up to these 12-bit oscilloscopes no problem in high-res mode, which is of course, directly speaking, plain bullshit. Because there's no way, I mean, you can do nice things with a high-res mode, but a high-res mode doesn't give you more quantization steps. if you're measuring a European voltage around 240, 250 volts with an 8-bit scope, you can't detect anything smaller than 1 volt, which is the smallest quantization step that you have left. Now, with a 12-bit scope, you get 16 times more resolution. And in that case, in the same scenario, you could still resolve 1/16 of a volt, which is, I think, 62.5 volts. Yep, sounds about right. Millivolts, sorry, 62.5 millivolts. And that's a completely different ballpark. Now, you already see the problem. If you can measure much smaller voltages and much smaller change in voltage, you need to prevent noise. If you're catching any noise right here that's not actually in the signal, you got a problem, because you're going to screw up your measurements, and people are going to be trying to reduce noise that isn't actually there, and your effective number of bits, big marketing buzzword, will be significantly reduced. Now let's open this can up and see what's underneath. And I still apologize for the shakiness. I'm really just filming this with my hand here. Now let's zoom in and get into the channel 2 section here. Looks really nice. I mean, you really have to say for the entire board, it's very neatly routed. Teledyne LeCroy really did picture book work on laying this design out. I have to say, I'm very impressed by that part. Now, I found one budge. If you go up here in the channel 1 section, you see this little connector down here, and apparently they screwed up, I guess, a clock signal. And let's see if the camera focuses on that. Oh yeah, nice and beautiful. You can see that somebody botched that on there. And well, I mean, I guess you can't say much about that, nothing bad at least. They made sure that the mechanical stability is there. They nicely strapped it to each one of those covers of the ADCs, and apparently they prepared for possible budges. We'll just happen to have a test pin there or whatever. I don't know. I guess nobody really plans budges, but maybe they did. If they did, I'm really impressed, because that's something every engineer should be prepared for. I don't know of very many engineers that pop out a working PCB the first time they try. There are so many PCB revisions until you have a fully functioning product, and this oscilloscope was one of the first few that left the factory. So you would think that there's probably some sort of hardware revision either already in place or coming up very soon. At least you'd hope that. Alrighty. Now, the ADCs are unfortunately hidden, and I can't get in anywhere there, even though I'd love to look at it. But a little bird tweeted me and told me what's inside is a Texas Instrument ADC 12D1600. That's a 12-bit, 3.2 gigasamples per second RF sampling ADC. Now the scope only has a sampling rate of 2.5 gigasamples per second, and I say only solely to reference that is less than what the ADC is capable of. 2.5 gigasamples per second is quite a bit of horsepower, and I love this scope so far. I haven't gotten around to writing an actual review, but I thought the teardown is a very nice way to start. And let me zoom a little bit over the board here for you guys to look at. Maybe you spot something you want to talk about, or you want to ask questions about. By the way, I saw an ATtiny chip somewhere around here. I don't remember where it went. Let's see, maybe I can find it with bare eyes. Of course not now that I'm looking for it. Oh, there it is. See if the camera zooms on the text. Not zooms, focuses. Yeah, there we go. Little tiny ATtiny. Very nice chips, by the way. Zoom a little bit more over the board. By the way, I don't know if you've noticed, but there's a big spot here in the back corner of the oscilloscope where there are provisions for parts, and I wonder if those parts are the difference between the HDO4000 and the HDO6000 series. I know the computer mainboard is a little bit different. The 6000 series has more horsepower on the PC side, but I don't think there can be that many differences on the acquisition board side. I mean, this one has anything that the 6000 series has, it seems. But who knows, maybe those parts have something to do with it. Oh yeah, one thing I forgot to mention. I'm really surprised that Teledyne LeCroy did not shield this RF section over here at all. I can clearly see a 125 megahertz peak if I perform an FFT on an open input, and even with signals on there or a perfect termination, I see these 125 megahertz from the oscillator. Not only that, I actually see a 625 megahertz harmonic on any channel, and I mean, so far it hasn't bothered me, but it's something they may want to consider, because after all, this is a 10 grand scope. You should be able to put a, I don't know, 40-50 cents, if that much, shield on there. Maybe a great idea for a future revision. But aside from that, and this little botch over here, I didn't find anything to complain about. Nothing really. Maybe you spot something. If so, let me know down in the comment section.